Hello students, welcome to Sri Chandra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 3 of our unit Magnetism and Matter. Let's begin with today's class. In today's session, first we are going to discuss about the time period of oscillation of a magnetic dipole. So let's begin then. We are going to discuss about the time period of oscillation of a magnetic dipole when it is placed in uniform magnetic field. So let's begin that let's understood that m would be the magnetic moment of dipole and b is the intensity of magnetic induction. If if it is suspended that, or if we can suspended magnetic dipole or pivoted, a compass needle makes a small angle theta from the equilibrium position, then the restoring torque on the dipole that we understood as torque equals to m into b into sine theta. This situation has been representing in the diagram that this is my dipole. This is south pole, this is north pole. We have just demonstrated from the compass needle, and this is from south, this is north. So it is the direction of m, and this angle is theta, so this could be angle theta. So when I rotate it, when I just suspend it with a string, then it will be having certain angle theta, and if we try to rotate it certain angle theta from its equilibrium position, then it will be having a restoring torque, and that restoring torque could be written as mb sine theta. Now this torque produces an angular acceleration alpha 1 opposite to the angular displacement theta. So if I can write I is the moment of inertia of the magnet, then I alpha could be written as equals to minus of mb sine theta. When I say I into alpha, I mean it's an alpha could be written as d square theta by dt square, and that would be equals to minus of mb sine theta. The negative sign indicates that the angular acceleration is opposite to angular displacement, and if we consider the theta is very small, then sine theta approximately equals to theta, and this equation can be written as it's an I d square theta by dt square should be equals to minus of m into b into theta, or I can write like this, it's a d square theta by dt square that should be is equals to minus of mb by I into theta. Now this d square theta by dt square would be the alpha, that is equals to minus of mb by I into theta. I hope this is clear. If you remember the oscillation class 11, that you we used to have a two kind of acceleration. One was the linear acceleration, another is the angular acceleration. Same way we have a two SHMs. One is the linear SHMs, linear simple harmonic motion, and the one more was the angular SHMs. Yes, so condition for linear SHMs was a is equals to minus of omega square x, and condition for angular SHMs was alpha is equals to minus of omega square theta. I hope this is clear. So as the angular acceleration alpha is directly proportional to the angular displacement, and it is directed towards the equilibrium position, the magnet will perform angular simple harmonic motion. It's an SHM. So we are just comparing this relation d square theta by d square dt square, which is equals to alpha equals to minus of mb by I into theta, with a necessary condition of the SHM, which is alpha is equals to minus of omega square theta. So if I compare it well, what I can have is the omega square that should be is equals to mb by I. Omega could be replaced with 2 pi by t, while t is the time period of the oscillation. So this could be written as 4 pi square by t square, that should be is equals to mb by I, and this t square should be is equals to 4 pi square multiplied by I by mb, and this t would be equals to 2 pi under root of I by mb. I hope this is I hope this is clear. Is it clear? So this is the time period when any bar magnet or any magnet is suspended in a uniform magnetic field. This is the time period of the angular oscillations. I hope this is clear. So we can say time period of vibration T would be equals to 2 pi under root of I divided by m into bh. While I write this bh because we are talking about the horizontal magnetic field. Yes. Now what is I? What does it? So when we say I, we mean it's a moment of inertia. And in most of the situations, it was the bar magnet. Most of the situation, it was the bar magnet. So, and this is the length of a bar magnet. This is the breadth of a bar magnet. So when I say moment of inertia, I must write I is equals to m into bracket L square plus b square by 12. Yes, this is the moment of inertia of the bar magnet above the axis of oscillations. M, M is the mass of the magnet, where L is the length of the magnet, B is the breadth of the magnet, and BH, this is the horizontal component of Earth's magnetic field. Yes. Now I want to add one thing, that when we discuss that this is the bar magnet, this would be the length, this would be the breadth. In most of the cases, in most cases, we consider bar mag we considered thin bar magnets. So moment of inertia, moment of inertia of these bar magnets can be considered as I is equals to ml square by 12. Yes, so we can consider, because in most of the cases we are going to consider that those are the thin bar magnets. That is not going to be specified, but that is to be understood. So if they want that length and breadth both should be covered, both should be written, they will mention it specifically. Yes, otherwise you can take this I, which is equals to ml square by 12. Is it clear? So now let's discuss the relation that I have derived. It is that T is equals to 2 pi under root of I divided by MB. This has dependence of T is directly proportional to the root of I, while I say M and B is constant. This has square root of inversely proportional of M. It's a magnetic moment. This is the case when I consider that I and B is constant. And one more, it's a T inversely proportional to the root of B. T inversely proportional to the root of B, while I say I and M is constant. So this is the situation where I can relate this. Now let's suppose they have given that, let's suppose they have given that if we make a certain variations, if we make certain vari if we make a certain variations in the different parameters, what would be the change in the time period? So if says that if moment of inertia of a bar magnet changes by 2 percentage, find out change in the time period of oscillation. So what will you do? Look at this. They said that moment of inertia mi of a bar magnet changes by 2%. You can consider that this is the variation of 2% only, and when the variation is less than 5%, we are allowed to use the relations given by the errors. So they have changed by the 2% only, so we can use the relations of the error, and if we can use this, we have this relation t directly proportional to the root of I. We can write it's a delta t by t, that should be is equals to half into delta I by I. So this delta t by t could be written as 1 by 2 multiplied by 2 percentage. And while I say 1 by 2 into 2 percentage, this delta t by t could be written as the 1 percentage. I hope this is clear. So there would be the change in the time period by 1 percentage. Does it clear? Does it? Are you sure? Are you? Great. Let's have one more question, that if magnetic dipole moment is increases by 4 percentage, find out change in the time period of oscillation of bar magnet. So if magnetic dipole moment is increased by 4 percentage, find out the change in the time period of oscillation of bar magnet. This is the requirement. So this t directly proportional to the 1 by root of m, and while I doing so, it's a delta t by t should be equals to minus of, why minus, because these two are the inversely proportional, it's in half into delta m by m. So that should be minus of 1 by 2 multiplied by 4 percentage. And while I write this, it is the delta t by t, that would be equals to minus of 2 percentage. This is delta t by t. This is, so the time period has been decreased because this has increased. So this is but obvious that this is to be decreased. Yes. So this is to be decreased by 2 percentage. Is it clear? Great. Let's work for the next question. It says that if moment of inertia of a magnet increases by 4 percentage, and and magnetic moment decreases by 3 percentage, find find percentage change find percentage change in the time period of of oscillation. So now think before you act and tell me what is to be done, what you are supposed to do. It says that moment of inertia increases. So this is t directly proportional to the root of I divided by root of m. So it says that moment of inertia of a magnet increases. So this has increased. So in respect of that, time period will increase. And magnetic moment decreases. So if this is decreasing, this means this is going to be increased. So it will add to this part. So we can write this as delta t by t could be equals to 1 by 2 into delta I by I plus 1 by 2 into delta m by m. I have added both because as this is decreasing, because t is inversely proportional to the m. If m is decreasing, then t must be increases, and t and moment of inertia both are or not directly proportional. So when they are directly proportional, if I increases, t definitely increases. So this is the situation. Now delta I by I, that is given by 4 percentage, so it's a 1 by 2 into 4 percentage plus 1 by 2 into 3 percentage. So this is 2 percentage plus 1.5 percentage. This is equals to 3.5 percentage. This is delta t by t. This is equals to 3.5 percentage. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Are you sure? Great. Do you have any issue up till now? Anything? Any doubts up till now? Do you have anything? Any doubts? Do you have any doubts? Any? No? Great. So now let's look at the next questions and next situations. We are going to discuss a different cases based on which time periods can be changed. Yes, so let's discuss them one by one. It says that a magnet is oscillating in a magnetic field B and its time period is T. Now we can say if another identical magnet is placed over that magnet with unlike poles together, then the time period. Yes, so the situation is that let's suppose this was the initial situation. This could be said as this is the south pole, this is the north pole, and another identical magnet has been placed over this, and they say they're unlike poles together. This is south, this is north. So if I say this is south, this is north, this would be the magnetic momentum 1, this would be the magnetic moment 2. Yes. Now what we are having is that initially this t should be is equals to 2 pi under root of I divided by mb. While I write down the t dash, while writing down the t dash, I should write it's a 2 pi divided by, they said identical magnet, so moment of inertia of this is I, moment of inertia of this is I, and as moment of inertia is a scalar quantity, I need to add it. It's a 2I divide by m minus m divide by m minus of m, because this is m net into b. As this m minus m is 0, this t dash tends to infinite. Yes, that's why they say the time period becomes infinite. I hope this is clear. Is it clear? Is it? Are you sure? Great. Next, it says that a magnet is oscillating in a magnetic field and its time period is t. If another identical magnet is placed over that magnet with similar poles together, then the time period. So the situation is that initially t should be is equals to 2 pi root of I divided by mb. Yes, and the situation is that this is one of the bar magnet, this is south, this is north, this is another bar magnet, this is another bar magnet, this is south, this is north. This is the magnetic dipole moment of first magnet, this is the magnetic dipole moment of second. This is having moment of inertia I, this is having moment of inertia of I. So let's calculate the t dash. The t dash could be written as 2 pi root of, it's an I net, it's a I plus I 2I divided by m net, it's a 2m into magnetic field remain the same. So this 2 and this 2 has cancelled out. So I will be remain with the t dash is equals to 2 pi under root of I divided by mb. And when I have been left with this, it is just the t dash. is equals to t. Got it? Yes? Yes, no. Great. Next. Next. It says that if a magnet having time period t in VMM, it stands for vibrational magnetometer. Yes, please do remember this because we are going to use this as a certain device to measure certain time periods or to find out the magnetic field of particular location or to find out the magnetic moment. So it's a device, vibrational magnetometer, that if a magnet having time period t in a VMM is cut into n equal parts along axial line and one of the part is used in VMM. So let's have a look. This bar magnet was there and it has been divided into n equal parts. So these are the n equal parts. So now if I have to taken one of the section, then the m dash of this one of the section would be equals to m by n. Yes, first thing. Next, what I'm having is that t should be is equals to 2 pi root of I divide by m into p. This is t dash t is equals to 2 pi under root of I by mb. So this is the one variation. This is the first variation. Now next variation for the moment of inertia. Moment of inertia could be given as I is equals to ml square by 12. So my new mass, it would be the total mass m divided by n. But as I can see that length of this magnet remains as it is. As length remains as it is, so I can write it's an L dash. L dash could be equals to L only. So now if I took a ratio of this situation, then T dash should be is equals to 2 pi root of I, which is equals to ml square by 12, in which L remains the same, 12 always remains the same. So this would be I directly proportional to the L, it's a I by N multiplied by, sorry, it's an M dash, it's the M by N into 1 by B. I hope this is clear. When I write this N and this N has cancelled out. So I have been left with the 2 pi root of I divided by MB. And this is equals to T. Is it clear? Is it clear? Yes. It's an I dash is equals to I by N. Got it? Have you? Are you sure? Are you sure? Do you understand this completely? Do you? Great. Now, let's suppose in the previous case we made a certain modifications that if a magnet having time period t is cut into equal parts perpendicular perpendicular to its length, then time period of any one of the part will be the time period of any one of the piece will be. So what can I do for this? If a magnet is having a time period of t and it is going to cut into equal parts perpendicular to its length, I need to find out the time period of any one of the piece, what it would be. So what I need to understand is that this was the magnet and now it is going to be divided into this many parts. We say it's an n equal parts. So when I divide this into n equal parts, write down all the variations. First, magnetic moment will be changed, and it would be changed by m by n, that we have derived previously, that when magnet has been cut it down into n segments perpendicular to its length, then this magnetic moment has been changed by n. It's an m dash is equals to m by n. Now, next, other than this, I am having a moment of inertia which is equals to ml square by 12. So my mass has been changed. It's an m dash would be equals to m by n. Even this time length has been changed. So this L dash is equals to L by n. So mass has been changed, length has been changed. So new moment of inertia would be is equals to m dash L dash square divided by 12. That could be written as m dash would be equals to m by n multiplied by L dash. L dash could be written as L square by n square into 1 by 12. So this I dash, look at this. This ml square, this 12 was the initial value. So this I dash could be written as I divided by n cube. Yes. So this I dash is equals to I by n cube. So let's just write it down, that t dash should be is equals to 2 pi root of I dash divided by m dash into p. This could be written as 2 pi under root of I dash. I dash could be written as I by n cube. M dash could be written as m by n, and the b remains as it is. So if this is the case, then this is n, this is the cube, that means only the I have been left with the square. So this could be written as t dash. It is a square, take it out of the square root, it's a 2 pi root of I divided by mb whole multiplied by 1 by n. When I look at this, this was the initial time period. So this t dash should be is equals to t dash, that should be is equals to capital T divided by n. I hope this is clear. Does it? Does it clear? Do you find this interesting? Are you sure? Yes. Are you sure? Great. So do you understand these things? Yes, when and when they have been placed like this time period will be divided by t by n. Yes? Great. Now let's do one more special case, that let's suppose magnet has been divided into this by x equal parts, into this into y equal parts. If initial time period is t, if initial time period is t, find out time period of any one piece. Yes, when and when we are talking about this, we always consider that they have been placed in the same magnetic field. So every time we are not just mentioning it, but you must understand that if magnetic field is going to change, I will let you know. If I have not tell you anything about it, that means it is going to be constant. I hope this is clear. Great. So let's start doing this. What all parameters are going to be changed? First thing, it's a magnetic moment is going to be changed, which should be m divided by x into y. Yes. Next, we are having I is equals to ml square by 12. So we would be having I dash, which is equals to m dash L dash square divided by 12. So this mass is going to be changed by m into x into y. The length is going to be changed. The length is going to be changed by L by y. I hope this is clear. and 12 remain as it is. That you understand. Great. So I dash should be is equals to m dash l dash square divided by 12. That would be equals to 1 by 12 as it is, multiplied by m dash, which should be written as m by xy, multiplied by l dash square. That should be is equals to L square by y square. So if I keep it aside, it's an ml square by 12, ml square by 12 multiplied by 1 by x into y cube. This is I dash, and that could be written as this ml square by 12. This ml square by 12 would be as it is. So this is I by x y cube. I hope this is clear. Is it clear? So let's try to write it down. It's a t dash that should be is equals to 2 pi root of I dash divided by m dash into b. This is equals to 2 pi under root of I divided by, it's an xy cube, multiplied by m dash. The m dash could be written as it's an m into x into y into this is 1 by b. Got it? So let's just rearrange this. This is equals to I by mb multiplied by this x, and this x can be gone. This y, this is y cube, so only I have been left with the 1 by y square. Keep it aside, it's a 1 by y square. So when I write 1 by y square, it is 2 pi root of I by mb into 1 by y. So this is equals to t dash is equals to t by y. Y is the number of segments which is perpendicular to its length. So this t dash could be written as t dash equals to t by n. Does it clear? Does it? Are you sure? Are you sure? Got it? Great. So can it be done? Now will you capable enough to do the variations? Are you sure? Are you? Great. Let's see this. It says that two magnets of magnetic moments m1 and m2, while m1 is considered as greater than m2, are placed one over the other if t1 is the time period when like poles touches each other, and t2 is the time period when unlike poles touch each other, then in sum and difference method. Now what is sum and difference method, that I will let you know. But before that, what I need to do is let's just find out the time periods. That they said that t1 is the time period when like poles touch each other, and when t2 is the time period when unlike poles touch each other. So according to the given data, they says two magnet moments of m1 and m2. That means they are not the identical magnets according to their magnetism, but according to the moment of inertia it will be the same. I hope this is clear. So when like poles touch each other, t1 is the time period when like poles touch each other. It's a, let's suppose this is north 1 south 1, this is north 2 south 2. So for this is m1. For this is m2. This m net would be equals to m1 plus m2, and the I net, moment of inertia, it is 2i. Is it clear? Is it? Is it clear? Great. Next, when unlike poles touch each other, this is north 1 south 1, this is south 2 north 2, this is m1. Let's say this is m2. As they mention, m1 is greater than m2, so my m net would be equals to m1 minus m2, and I total, I should say I, not I net, I should say I total. So the I total would be equals to 2i. Yes. So now what I need to understand is that I am having a t which is equals to 2 pi root of I by mb. So what is changing? Look at this. Look, 2i remains the same. Magnetic field remains the same. So only the change is with the m. It's a net magnetic moment. So what I need to write is that t1 divided by t2, that should be is equals to, m net 2. This is m net 2 and this is m net 1 divide by m net 1. I hope this is clear. Is it clear? So this is just the ratio of the time periods, and let's have a look that we need to reach at the sum and difference method. So we are heading towards it only, but let's have a look first. It's a t1 is to t2. When like poles touches each other, it is a t1, that could be written as m1 plus m2, and when unlike poles touches each other, it's a t2, so that could be written as m1 minus m2. I hope this is clear. So this is the ratio of the time periods. Now let's just square this. It's a t1 square plus t2 square. That should be is equals to m1 minus m2 divided by m1 plus m2. Now what I supposed to do is let's I need to calculate the m1 is to m2. How could I get it done? How could I get it done? How could I? What I'm supposed to do so that this can be done? What can be done? Yes. So what I'm supposed to do is let's have this relation. It's a t1 square plus t2 square divided by t2 square minus of t1 square. That should be written as m1 minus m2 plus m1 plus m2 divide by t2 square minus t1 square. It's an m1 plus m2 minus m1 minus of m2. So this is t1 square plus t2 square divide by t2 square minus of t1 square. That would be equals to when I say m1 minus m2, this is m1 plus m2, this minus m2, this plus m2 should be cancelled out. M1 plus m1, it's a 2m1 divide by this is m1 plus m2 minus of m1 plus m2, so it's a minus of m1 and plus m2. This is equals to 2m2. Yes, I hope this is clear to you, that t1 square plus t2 square. Is it clear? Great. So this is m1 by m2 could be written as t1 square plus t2 square divide by t2 square minus of t1 square. This is the sum and difference method. I hope this is clear. Initially what you have read it, that what would be the sum and difference method. This is just the sum and difference method, and this would be the value of magnetic moment of first magnet to the magnetic moment of the second magnet. Yes, if I want to write down this relation in terms of the frequencies, let's have a look. It's an m1 is to m2. That would be equals to 1 by f1 square plus 1 by f2 square divide by 1 by f2 square minus of 1 by f1 square. If this is the situation, then what I can have is the it is the m1 divided by m2. That should be is equals to f2 square plus f1 square divide by f1 square minus of f2 square. This is the ratio of the m1 is to m2. I hope this is clear. Does it clear? Any issue, any concern, any doubts? Is there anything? Is there anything? Is there anything? Yes, no, no. Great. So, are you clear with this? Are you clear with this? Can we move to the next case? Can we? Can we move to the next case? Are you sure? Let's move on. Let's suppose the next case is that if some bar magnet is placed in the two different position of magnetometer which are having their horizontal magnetic field BH1 and BH2. So I need to find out the ratio of the time period. Now in this situation, they are having everything same except the magnetic field. So what I'm understood is that this is the relation, this is equals to T is equals to 2 pi root of I by MB. Only I have been changing, it's 1 by root of B. It's a 1 by root of B that I am changing. So if I'm going to change this only, if I'm going to change this only, then what I can have is this is the T1 divided by T2. Let's assume that this is the BH1. So this is equals to BH1 to the BH2. That's it. You did it. Great job. Are you clear? Yes. Are you clear? Is that clear? Is that any concern? Is there anything? Are you sure? Are you sure? Yes. Now let's look at the next and last cases. Let's look at the next and the last case, that when certain situation happens. Let's suppose the given data is that if two magnets having magnetic moments m1 and m2 are placed one over the other such that first, like poles together. I will assume that this time period is T1. Second, unlike poles together. I will consider this time period as a T2. And the third, their axes are perpendicular to each other. This is T3. So they want find the ratio of the time periods. Find out the ratio of their time periods. B is same. That is given. So how will you do this? How will you do this? We have done with the like poles and unlike poles, but this is new for us to keep them perpendicular to each other. So let's just look. We have this relation. It's a T is equals to 2 pi root of I by MB. Only the thing I'm keep changing is the magnetic moment. So my relation would be T directly proportional to the 1 by root of M. Now for the first case, when like poles together, it's a case of the like poles. So when it's a case of like poles, something like this, it's a south, it's a north, it's an S2 N2. So this M net would be M1 plus M2. In this case, second case, it's an unlike poles. So this is south, this is north, and this is the case when this is north 2, this is south 2. This is M net, which could be written as let's understood that assume that M1 minus M2. M1 is greater than this, and the third situation where these two are perpendicular to each other. So this is the case. Yes, this is S1, this is N1, this is S2, this is N2. So this M net should be root of M1 square plus M2 square. Got it? Are you sure? So what you need to do is it's a T1 is to T2 is to T3 should be equals to, yes, should be equals to, what you need to do is just have a ratio of this. It's a 1 by root of m. So this is equals to 1 by root of m1 plus m2 is to 1 by root of m1 minus m2 is to 1 by root of 1 by root of, again it's an m1 square plus m2 square. I hope this is clear. Does it clear? Does it any any difficulty over this? Is there anything? Is there anything? No? So will you be ready for the questions? Will you be ready for the questions? Are you sure? Can we do it? Can we? Can we do it? Let's start then. Let's be ready for the questions. Let's have it. The first question says that the data is that two bar magnets placed together in VMM, it's a vibrational magnetometer, takes 3 seconds for one vibration. If one magnet is reversed, if one magnet is reversed, the combination takes, this combination takes 4 seconds for one vibration. Find ratio of magnetic moments. So this is the requirement, that two bar magnets are there, and if they are placed together in a vibrational magnetometer, they takes 3 seconds for one vibration. And if one of the magnet is reverse, that means initially the situation could be like this, that initially the like poles are together, it's an S1 N1, this is S2 N2. Yes, that I understand. T is equals to 2 pi root of I by mb. If m increases, T decreases. Now in this case T increases, that means m must be decreasing. So initially the like poles may be together, and then this is the case of time period of 3 seconds for one vibrations. For one vibrations it takes 3 seconds. And next it was the case that it's an S1, this is N1, and one of the magnet is reverse. Let's This magnet has been reversed, it's an N2 N2. Yes, this was the case of T2, that would be equals to 4 seconds. So we have derived this to find out the ratio of M1 is to M2. The relation was M1 is to M2, that should be is equals to T2 square plus T1 square divide by divide by T2 square minus of T1 square. Yes, so this could be written as it's a 4 square plus 3 square. This is square. Yes, 4 square plus 3 square divided by 4 square minus of 3 square. So this is 9 or 16 plus 9, it's a 25 divided by 16 minus 9, it's a 7. This is M1 is to M2. If I take a ratio, it's a 7 threes are, yes, 3.5 something, probably 3.57. I hope this is clear. Is it clear? Is it Have you got the same answer? Do you? Do you have the same answer? Great. So ready for the next question? Ready? Let's have a look. The question says that a bar magnet makes 40 oscillations per minute. 40 oscillations per minute in VMM. Now, an identical magnet is demagnetized completely and is placed over the magnet in VMM. Calculate the time taken for 40 oscillations by this combination. So what I need to do, what is supposed to be done? First thing, go through the data very carefully and think before you act that what is to be done. How could I do this? How could I do this? So what is to be done is, this is that first thing they are talking about number of oscillations per minute, so they are talking about the frequency. We have a time period which is equals to 2 pi root of I by mb, and for frequency I can write like this, it is 1 by 2 pi root of mb by I. So if I understood that what all has changed is the magnetic moment has been changed and moment of inertia has been changed. So if these two are changing, if these two terms have been changed, then I can write it's a frequency that is directly proportional to the m by I. Now the thing is what they have supposed to do is that initially they are having only one magnet. So their I dash, let's say I1, let's write it down, it's an I1. One second. Yes, This I1 is equals to I, and this M dash is equals to M. Now finally, what they have done is that this is, let's say, south north. This was the initial magnet, south and north, and this is unmagnetized magnet. It is the demagnetized. That means it is not having a magnetic property, but it must be with its moment of inertia. I hope this is clear. This is the location where you are going to made a mistake. Please understood this, that if it is demagnetized, then it must not be having a magnetic moment, but it must be having the mass, it must be having the length. That means it must be having the moment of inertia. So I dash would be equals to 2I, and M dash again it would be the same. So even M dash is not going to change, only the I is going to change. I hope this is clear. So this is frequency 1 divided by frequency 2, that is equals to root of I1 to the I2. So this is root of I2, which is equals to 2I divided by I. The initial frequency to the final frequency, it's an F1 is to F2. So this has gone, and what I can write is this F1 square divided by F2 square is equals to 2. So this F1 square is to F2 square is equals to 2, and for this we can have a time period of this, that this is equals to T2 square divided by T1 square. T2 square divided by T1 square is equals to 2. So this T2 square equals to 2 multiplied by T1 square, or I should say it's a T1 should be equals to root 2 times of T1. Initially it takes 40 oscillations per minute. Now they will having a root 2 times per minute. It's an This is the answer. It's a T2 should be equals to root 2 times into T1. I hope this is clear. Got it? Are you sure? Are you sure? So could it be done? Could it be done? Are you sure with this? Got it? Let's move to the next question. The question says that the question according to the question that, let's suppose this is the bar magnet, and initially if it has been hanged up, this time period is T1. Now now this is, let's say, 10 seconds. Now this magnet has been divided in the segments into, let's say, 3 segments, and if any one of the part has been hanged up in a same magnetic field will be the same, then the time period will be T2. Now let's suppose this same magnet has been divided into, sorry, this is 4 segments, so in this 3 segments, this is time period T3. What I need to do, I need to find T2 is to T3. So what I need to do is that, let's suppose this T1 is the T 10 seconds, and this T2 is the time period when any one of the part or any one of the piece has been hanged up. So what I can do, it's a T2 by T1, and I understand that when this has been divided along its length, nothing is going to be changed. So this is T1, and this is T1 by n, which in my case is the T1 by 3. So T2 by T1, it is equals to 1, and T2, and I can write like this, it's a T3 by T1. For T3, it's a T1 by n into 1 by T1. So this is equals to 1 by n, which is equals to 1 by 3. Now what I want T2 by 3t. So could I write, it's a T2 by T1 multiplied by it's a T3 by T1, that is equals to T2 by T1. This is 1 is to 1. multiplied by T3 by T1. This is T3 by T1. It's an it's an T1 by T3 could be written as 3 is to 1. So this is equals to T1 by T3, which is equals to 3 is to 1. So this is 3 is to 1. This is the ratio of T2 is to T3. I hope this is clear. Is it clear? So now can you do all these questions? What actual situation is that there is a certain theory called as the vibrational magnetometer, and from that theoretical parts all this kind of questions can be asked. All this kind of questions can be asked. This is having very high weightage, having very high probability in the medical examinations, but in JE examinations this has been asked over almost 2 to 3 years alternatively. Yes, but from when segments have started, that means the JE is going to be conducted in many of these slots. These are the questions that is coming regular basis. So this is very important aspect, and this is very important topic according to the competitive examinations for medical as well as engineering aspirants. Yes, so just let's just wind it up this session over here. We have discussed the time period of a bar magnet when it has been hanged or when it has been suspended in a uniform horizontal magnetic field. This is all about the time periods, and we have seen the different variations that what could change the time period. Please go through this very seriously. This will help us to get this kind of questions done. Thank you. Have a good day. Take care.